Well, in any case, I think we can start now. Welcome to Algebraic Topology, very highly requested topic, actually. I guess because at some point when we're talking about topology in physics, everybody always gets bombarded with these homology groups, cohomology groups, whatever, and just are expected to know what that is. So I hopefully will be able to shed some light on that. Generally, algebraic topology is concerned with, well, in a way, classifying topological spaces up to homeomorphism, or at least up to what's it called? Up to homotopy equivalence. Yeah, and usually it is sort of quite easy to show that two topological spaces are homeomorphic. Namely, you just construct a homeomorphism, you just write it down, and then, oh yeah, so there is one, therefore they are homeomorphic. But the converse is really hard to prove usually. One sort of clever way to do this is to construct topological invariants. So quantities or properties of a topological space that are preserved under homeomorphism, or which we will see a bit later on under homotopy equivalence. And well, examples of these topological invariants that are a bit boring, let's say, are properties like connectedness, path connectedness, compactness, local compactness, local path compactness, whatever. Just because like those are properties of the topological space itself, so they should be preserved under homeomorphism. The problem is a bit that these properties are binary. A space can either have them or not have them. There is no sort of middle ground or no finer distinctions. And well, the basic idea is of algebraic topology is to construct topological invariants that are a bit more interesting than that. And well, usually we will be interested in properties that are not only invariant under homeomorphism, but also under homotopy equivalence. So I guess also after already speaking about homotopy in homological algebra, I should define what a homotopy in topology is. And we begin by, well, saying what a homotopy between two continuous maps is. That f and g from x to y be continuous maps between two topological spaces. And then a map h from x, Cartesian product with the unit interval, to y is called a homotopy between f and g, or from f to g, if, well, firstly, it should be continuous. Secondly, we would like sort of the restriction to one endpoint of this interval to be f, and the restriction to the other endpoint to be g. Now, this notion on its own is, well, I don't know, usually you also want a bit more. You usually also want to have a subset on which this map is fixed. Ux. So if we have a subset of x, And on this subset, our map stays constant. So for all t in that unit interval, we have, and for all x in that subset, we have that h of x and t is equal to f of x and also equal to g of x, logically. Then we say that this is not only a homotopy, but a homotopy relative to u. For example, something that occurs very often is if x is also the unit interval, then you're looking at curves, and you usually want to have those curves be homotopic relative to their endpoints. Yeah, but we will also see this a bit later on. Okay, so if there is a homotopy between two maps, between f and g, we call f and g homotopic. And denote this by what's it called, \simic. And if they are even homotopic relative to some set, if there is a relative homotopy, relative to u between f and g, we say that they are homotopic relative to u. And since, yeah, did I write that down? Well, and since you can sort of nicely glue continuous maps, the property of being homotopic, or the relation of being homotopic, is actually an equivalence relation. Same goes for relative homotopicness. I don't know. And yeah, I don't know. Equivalence relations. This will turn out to be somewhat important later on. Okay, and then we can again define for two topological spaces to be homotopy equivalent. If there are maps between x and y and a map between y and x, such that their compositions are again not equal to the identity but homotopic to the identity. And we note that, well, again, homotopy equivalence. Oh yeah, by the way, we write this as with the same symbol as homotopic. Again, homotopy equivalence is an equivalence relation. Sorry. And it is a lot weaker than homeomorphism, but like I said, eventually all of the things we construct here will be preserved even under homotopy equivalence. I guess you could ask a bit, why is that useful?
Do you know an example of two spaces who are not homeomorphic but homotopy equivalent?
Oh, of course, there are loads of them. For example, every, I don't know, star-shaped space, convex space, or whatever is homotopy equivalent to the point, but not the other way around, or like they are not homeomorphic. So I guess the intuition between homotopy is that you have two maps, and if you can continuously deform one map into the other, then they are homotopic. And well, equivalent, or like for homotopy equivalence, you have two maps and then you have their composition. And if you can continuously deform that composition into the identity, you are homotopy equivalent. I guess I drew some nice examples. If you have some space that has some hole, and you look at curves, so at maps from the closed interval 0, 1 into that space X, then you can like draw, for example, a curve like this and a curve like this, and ask, are they homeotopic? Are they homotopic? But the problem is that like asking if they are homotopic is quite a boring question, because we're allowed to move the endpoints. So we can just move this one around here and back there, and then similarly sort of move all the other points like that. And yeah, we've constructed a homotopy. So green and blue are homotopic. But the ideas that we've defined actually allow us to forbid this. We can just ask if they are homotopic relative to their endpoints. So we can draw them like that and say that our set U consists of those 2 points. So U, and this is the space X. Then however you would want to move this curve, like there's always this point that isn't contained in X, so like this hole, you would need to move your curve over that hole, so they are not homotopic. That is at least the intuition. Showing that they are not homotopic is a different thing. So conclusion are not homotopic relative to U. You could also do a similar thing if you don't consider like lines, so you don't consider maps from 0, 1 to X, but you could consider maps from the one sphere to X, so from the circle to X. And then when you then look at homotopies, you sort of don't say that any point should be fixed, but you say that at each point, or that like at each stage, it should still be a loop. And if you have a loop like that, like you can't move it over here. Maybe again, green and blue. Or I don't know, can't move it over here. Just because if at every point, if at every stage you have to be a loop, Like you would still have to move somehow over this abstraction here. So much for being homotopic and being relatively homotopic. Now for a couple of homotopy equivalences that we sort of use all the time. Firstly, we have R to the n and the set containing one point. So now how do we construct these maps that we need to define? So we have f from R to the n to the set containing one point. Well, I think at some point we have established that a singleton set is the terminal object of the category of, well, sets, I guess, and also of topological spaces. So there is only one map that we can define, namely just everything maps to that point. The other way around, we have infinitely many choices because, well, such a map, or let's say there are Rn many choices that we can use, but I will opt for just mapping it to 0. So if we now look at f after g, well, f after g goes from the singleton set to the singleton set. Yeah, okay, it maps the singleton to singleton, so that is actually equal to the identity on the singleton set. Okay, nice. The other way around is a bit more interesting, because what does it do? It maps Rn to Rn, and it maps every point in Rn first to the point and then back to 0. So it maps everything to 0. Now, can we show that this is homotopic to the identity? Yes, we can. And I guess I will just define some homotopy for you, and you can tell me if you believe me that they are homotopic. We have a point in Rn and a number, and we map them to x times 1 minus t. So what are the three axioms? Should be continuous. Yeah, I think so. Secondly, if we restrict it to 0, to t equals to 0, then we should have one of the two maps, namely x maps to x. So we have the identity on Rn. And for t is equal to 1, we have x is mapped to, well, x times 1 minus 1 to 0. So that is equal to g after f. So H is a homotopy between the identity and g after f. So g after f is homotopic to the identity. And, well, yeah, that shows that we have a homotopy equivalence. And generally, you can just show that in a convex or even in a star-shaped space, a very similar argument would hold true. So we can do that. And now, a second important example. We have Rn, but we take one point out. Rn minus the origin, and that one is homotopy equivalent to the n-1 sphere. So the set of points in Rn that have norm 1 Why is that the case? Well, we can map, I guess I'm going to speed things up a bit. We can map a point to, well, its normed version, and the other way around, you just map it to itself. Then you have, when you go in that in this direction, you have the identity, and when you go in this direction, you're still mapping x to x over norm of x, but you can show that sort of they are homotopic to the identity because you can just move that one out along the ray, or I guess inside along the ray. Just need to rescale the norm, or you just need to interpolate like linearly. Okay, now we are going to sort of try and construct a couple of invariants. And the first one is relatively straightforward. So yeah, let X be a topological space. Define, I've called it capital pi of X to be, well, the sets of paths modulo homotopy relative to the endpoints. This is sort of what we have already hinted at. So yeah, paths, and we consider them to be equal if we can continuously deform them. And this thing, the set, which doesn't really seem that, or I don't know, seems way too big, like it encapsulates all the information, and in a way does, but it certainly has a bit more structure than just being a set, because it turns out we can concatenate paths. So we can define an operation on equivalence classes of two paths. We call this concatenation of the paths. And this is a path just defined by saying that, well, it should walk through gamma 1 at twice the speed for t in the interval 0, 1/2. And then it should go through gamma 2 on the interval -1/2, 1. And the inverse, gamma inverse, well, we define it by just walking through a path in the opposite direction. So t is mapped to gamma of 1 minus t. The set pi turns into a group void. Now, what is a group void? So we would like it to be a group, but the thing is, and maybe some of you already noticed it, like you can only concatenate the paths if at the point 1/2 those functions are actually equal. Or in other words, you can only concatenate a path. You can only concatenate two paths if one of them ends where the other one begins. Like walking through this one and then walking through this one doesn't define a continuous path. It's just not continuous. So you cannot compose every two paths. And that is why it is a groupoid and not a group. Basically a group, but where you just require the group operation sort of to not be defined for every two things. And this groupoid is called the fundamental groupoid.
Philip, one question here.
Yeah.
Does the speed matter? So when we will try to prove associativity in this case, what is going to end up happening is that it will be like 4 times and twice, right?
Yeah, so the thing is, because we did homotopy, the speed doesn't really matter. So in general, I mean, the speed matters up to the fact that we say you should have traversed it in like 1 unit of time, but that's everything. Like if you have a path gamma and a path gamma, like gamma composed with f, where f is some sort of reparametrization, then they are homotopic. So with f of 1 is 1 and f of 0 is 0. Then they are homotopic just because you can build a homotopy by interpolating between the identity and f. I don't know how much I should. Like you could define h of x and t to be gamma of, and then you have x times 1 minus t plus f of x t. And when you have t is equal to 0, then you just have, so t equal to 0, then you have just gamma of x. And if t is equal to 1, then you have gamma of f of x.
So basically any reparametrization is fine.
Yes.
So it's just the distance that is covered that matters. Like the path
not
is
the distance, like the so what matters is sort of how the curve winds around holes, and yeah, basically that.
Okay, yeah, I get it.
Yeah, and the homotopy is a very important thing, also because you need to prove that your operation is associative. And I know everybody likes associativity proofs, but sort of if you didn't have that homotopy there, then you would have something like gamma 1, gamma 2, and then gamma 3. This thing would sort of go through gamma 1 in 1/4 of the time, gamma 2 also 1/4 of the time, and then gamma 3 1/2 of the time.
No, that's the exact reason I asked the question, because I knew this would happen. Like,
yeah, that is exactly why we have homotopy, or why we're only looking at things up to homotopy to make things associative. And again, relative homotopy, or homotopy relative to the endpoints, because otherwise all two paths would just be homotopic if they lie in the same path component. And I guess second lemma, pi is actually a functor because let f between two let f be a continuous map between two spaces, then f induces a map of the fundamental groupoids. pi of f, or the push forward of f between pi x and pi y, just by taking a curve and mapping it to f composed with that curve. So you have a curve to x, and then you just map it to y, satisfying, well, the push forward of the identity is just the identity, and the push forward of a composition is the composition of the push forwards. So yeah, pi is a functor. And I guess you could have guessed it by now, but actually, if f is homotopic to G, then these push forwards are equal, because basically you can just compose with homotopies. I don't know, would you like to see the proof?
No.
Okay. And well, this then shows that if x and y are homotopy equivalent spaces, then their fundamental groupoids are isomorphic. So yeah, we've done it. We've constructed a admittedly very unwieldy topological invariant, or even homotopy type invariant. Well, it's not very, may not be very descriptive. So we're now defining well, sort of a sub-object, namely the beloved fundamental group. So if we pick a point in that set, or in that topological space, then we can define pi1 capital X small x to be, well, those paths in capital pi of x such that, well, their endpoint, or that, yes, that they are loops around x. So both endpoints are just equal to small x. The fundamental group. At the point x. Alternatively, we could also say that we have loop spaces, or that we consider loops, and this will ultimately be the definition that can be more generalized. Yeah, I don't know. So we could also say that we have maps from S1 to X that map some distinguished point to our point X. And when we consider that again, modulo homotopy relative to some distinguished point on the one sphere, or like the circle. Now we don't have that obstruction anymore, that we can't compose every path. So we indeed have a group. And now it's not that hard to show that sort of if you can find a path from one point to another point, then the fundamental groups at those 2 points are isomorphic. So eventually we will see that the fundamental group pi1 just depends on the path component that some small x is in, and not on small x in particular. And yeah, in a way, we can again see that the fundamental group is also a functor, but this time you consider sort of pointed topological spaces and then pointed maps, meaning that like the objects are topological space and a point inside that space, and the maps are continuous maps that map the distinguished point to the other to the distinguished point. Yeah, I guess conclusion. Capital Pi and pi1 are topological invariants that are even homotopy invariant. Now, all of these are sort of nice definitions. You can get behind them, understand what they are supposed to mean, but like they are still very hard to calculate. I've said before that it's like not very easy to show that two paths are not homotopic. And if you can't even show that two paths are not homotopic, like how are you ever going to determine the fundamental group of some space? So like computationally, it's not very easy. And so usually you're working with covering spaces when you want to calculate that. But yeah. However, there's one nice result that tells you, well, on one hand, how to calculate the fundamental group if you can sort of compose, or if your space sort of made up of two smaller spaces. And on the other hand, it also shows you just how ugly some fundamental groups turn out to be. I guess first I have here a couple of examples that shouldn't really be much of a surprise to anyone. So convex sets or convex spaces. We have seen that they are homotopy equivalent to the set containing one point, so that the fundamental group of any such convex space is isomorphic to the fundamental group of the space containing just one point, but that is just the trivial group, because like every path is already constant, so nothing to be done, I guess. Then the one sphere, there sort of every loop can be uniquely characterized by how much it winds around the hole, so to speak. And yeah, that is called the winding number, and in that way the fundamental group of the one sphere is equal to the free group generated by one object, where we can just say that this path or this loop is the one that just goes around once. But already, if you, well, this is also homotopy equivalent to R2 with 1 point removed, we can, I guess, look at what does R2 look like when we remove 2 points. And then you can sort of contract everything to not one loop, but to 2 loops. So this thing is homotopy equivalent to the space consisting out of 2 loops that are glued together in 1 point, sort of by, if you have your points here, then you sort of push everything here outside, and everything outside you push towards one of the circles. And yeah, this thing already has a very ugly fundamental group, namely the free group generated by 2 objects, where one of them is just the loop going around here once, and the other loop is just going around here once.
Why is this ugly exactly?
Because, well, free groups are nothing you usually do much in group theory. Like they are automatically very much infinite, very non-commutative. I don't know.
Yeah, okay.
So yeah, this blue is A and green is B. Okay. Yeah, so as promised, one theorem that actually tells you how fundamental groups behave under gluing. It's called the Seifert-van Kampen theorem, or I guess Seifert-van Kampen theorem. So yeah, if X is a topological space, and we can cover X by 2 open subsets, where U1 and U2 are open and path connected. And if U1 intersection U2 is also path connected and non-empty, then X is also path connected. Well, big surprise, I guess. And the fundamental group of X can be described as the amalgamated product of the fundamental groups of U1 and U2, amalgamated over the fundamental group of U1 intersection U2. So what is this amalgamated product? Firstly, it is the big reveal answer to the question, what is the fiber coproduct in the category of groups? Yeah, enough said. No. If we can write our group U1 as generated or as a group like with generators and relations, and we can write pi1 of U2 also as a group with generators and relations,
How exactly did you write that pi1 of u1 cap u2 here? Is it under the star?
Yeah, it's sort of supposed to be under the star, like
So like
we
the
did with
tensor product.
tensor products.
Okay.
Yeah. And well, if iota I is the inclusion of, well, the intersection of u1 and u2 in ui, then we can write pi1 of x as a group generated by the generators ai and bi, with the relations of the first group and the second group. And the additional relation that, well, the push forward of I1 of gamma is equal to the push forward of iota 2 applied to, well, not gamma, but like the equivalence class of some path for every path gamma inside, I guess, the fundamental group of u1 cap u2. So
where are you exactly pushing forward to?
well, pushing forward to the fundamental group, like iota 1 is a map between topological spaces.
Okay.
And then iota 1 push forward is then a map between the fundamental groups. I can also call this map just pi1 of iota 1.
No, I get that, but I'm trying to wonder how the map exists.
You just compose, so you have a path. You have a path going from 0, 1 to u1 and intersection u2, and then you just compose this path with iota 1 and get a path in u1, and this path is now an element of the fundamental group of u1.
So it's just gamma dot I1.
It's just what, sorry?
It would just be gamma dot I1 in this case.
I1 dot gamma, but
I1 dot gamma, yeah.
Yeah. Oh, I've even now done an example of this.
Sometimes you wrote pi and sometimes you wrote pi1. Is there a distinction between?
Where did I write pi?
Or maybe I was just stupid.
I mean, I wrote capital pi before we did the fundamental group, yeah.
Okay.
Okay, so basic takeaway, like you get, if you have a, like if the conditions of the Seifert-van Kampen theorem are met, then your fundamental group turns out to be generated by the generators of one group and the relations of that one group, and the generators of the other group and the relation of that group, plus some extra relations. But like nobody says that the generators should commute or anything like that. So in general, you get a very highly non-commutative group. And I guess one example we can use to show this, or one example we can use this with, is to show that spheres are simply connected. Yeah, by the way, we call a space simply connected if its fundamental group is the trivial group. So one example would be we can write the sphere as like the a union of two hemispheres. Northern and southern hemisphere. For example, just say that those hemispheres are the sets where the 0th coordinate is smaller than epsilon or bigger or equal to minus epsilon for some epsilon bigger than 0 because we want them to overlap. Then we can sort of flatten those hemispheres. So they are homotopy equivalent to the n-1 disk, which is just the points in to the n-1 whose norm is smaller than or equal to 1. Well, they are not only homotopic, but they are even homeomorphic, just by using some square root stuff. This is now a convex set. So the fundamental group of those hemispheres is 0, or is the trivial group. And we have the intersection of those two things is, well, some strip around the equator. So that's at least homotopy equivalent to the equator, meaning to like a sphere of dimension 1 less. If n is bigger than 1, that sphere as n-1 is path connected. For n is equal to 1, we have the 0 sphere. The 0 sphere is just 2 points, so that's not path connected. But for anything bigger than that, it's definitely path connected. And I guess so are the hemispheres. So we can apply Seifert von Kampen, which shows that, well, the fundamental group of the n sphere is isomorphic to the trivial group amalgamated with the trivial group over anything, but that's just trivial group. Like we have 0 generators in that group, 0 generators in that group. So we still have no generators, so we have the trivial group. Well, in any case, it's still sort of tedious. You get very non-abelian groups that are usually not very nice to work with. So fundamental group and sort of the higher generalizations of that aren't really the preferred tool for algebraic topologists to work with. And I guess the tools that are more favored are the ones we're going to see after the break. Okay, so let's go on. So I guess a bit the takeaway from the studying the fundamental group is that it is sort of a fruitful idea to study maps from certain kinds of space, or like to study our topological space by looking at how some specified other space maps to it. In this case, it was just the unit interval, and the fundamental groupoid is in a way nothing else but the classifying all of the maps between the unit interval and our topological space up to certain relative homotopy. And now the kind of space we are going to look at now is going to be the space of n simplices, or not space of n simplices, but just the n simplex. And this is usually a kind of game that people like to play when they are doing some new lecture on algebraic topology, asking themselves how the lecturer is going to define the n simplex, because there are apparently two definitions. I'm going to use the one that I have encountered until now. Let n be bigger than or equal to 0, the n simplex is set delta n. So we have x in, well, Rn plus 1, such that all of the xi are non-negative, and the sum of the xi, so all of the components are non-negative, and the sum of the components is equal to 1. I guess the other definition just has them be a subset of n of Rn, and then say that the sum shouldn't be equal to 1, but like smaller than or equal to 1. And we can already define, we can define some maps between n simplices, namely the map di from the n simplex to the n plus 1 simplex for I being less or equal to, now how do I want to name these things? Yeah, I think 0 smaller than or equal to I smaller than or equal to n is just the map that maps x0 to xn to x0 to xi minus 1, and then insert a 0, and then xi going to xn. So this thing basically splits our coordinates in two, moves the right part one space over, and then inserts a 0 at that point. So I guess this can actually be smaller than or equal to n plus 1, right? Yeah. Because dn plus 1 just maps just has a 0 at the end. And we call this map the inclusion of the ith phase. The reasoning being the n simplex is sort of the simplest kind of polyhedron in every dimension, because it's basically just made up of triangles. And well, every polyhedron has some sort of faces, and you can number them, and this is how we define that. Yeah, so I guess we'll just have a look at a couple of simplices. So the 0 simplex is just one point, namely 1. The 1 simplex is the set of points in the two-dimensional real plane, such that the sum of their x and y components is equal to 1. So we have this line segment here. And the 2 simplex is, oh, this is going to be fun to draw. So we have R3. And then we have, well, yeah, then we basically have the plane where x plus y plus z is equal to 1. restricted to the positive octant. So that would then be that plane here. We can see it's an equilateral triangle. And I guess we can also look at the faces, because, well, I guess we can also look at the faces of every other thing. So the 0 simplex doesn't really have any faces. The 1 simplex has 2 faces. Yes, has 2 faces, namely the 0th face and the first face. And yeah, basically because for the 0th phase has a 0x component and the first phase has a 0y component. And now we have, if we label our axes as, let's say, x0, x1, x2, then the 0th phase has a 0x0 component. So that is md0. The first phase has a 0x1 component. So it is in the x2, x0 plane. And then this is md2. Yeah, and if we sort of go on from there, delta 3 will turn out to be a tetrahedron. Delta 4 will be, well, the 4 simplex corresponding generalization of that kind of shape in R3, sorry, in R4, well, something like that.
R5. Oh, doesn't matter.
Yeah. And, well, I guess these spaces are nice. We can see that sort of the fundamental objects that we maybe would like to be in there, namely points and line segments, are already contained in there. So I guess that's nice. But like, we don't want to look at these spaces. We want to look at maps from those spaces to some topological space we are looking at. So let X be another topological space, a singular n simplex is a continuous map from the n simplex to our topological space. And we can define the restriction to the ith phase.
We do not require injectivity. So
We don't require anything except that it's continuous. And that is, by the way, precisely the reason why it's called a singular n simplex. Because I guess in comparison to other simplices, we allow these ones to be all manner of non-injective and whatnot. And we can define the so-called restriction to the ith phase, d downstairs I sigma, to just be sigma composed with the inclusion of the ith phase. And also we call the set of n simplices, we call that Sxn. So we can now look at an example, namely the space that is the easiest to draw, R2. And now things can be as singular as we want them to be, which is nice, but also as curvy as we want them to be. Like, it's just a continuous map. It doesn't have to be straight, whatever that is supposed to mean. So like, this is a perfectly valid one simplex. Or let's say it is the image of a singular one simplex. We can more or less arbitrarily choose one of the endpoints to be d0 sigma and the other one to be d1 sigma. Yeah. Oh, by the way, this is just a singular zero simplex. And well, two simplex can also be like anything that has some kind of corners. Or not even that, but I'm going to do it that way. So this thing here is a singular two simplex. And I guess we can again define whatever boundary things we want to be the faces. So let's say this is d1 sigma. This is d0 sigma, and this is d2 sigma. And usually, yeah, I mean, because everything has to be I don't know how to put this, but like, since we're actually talking about maps and not just their images, we actually do have a lot more structure as what we can see here. For example, everything has sort of an orientation. We could say the orientation of this thing is, orientation of this thing is sort of this way. Then we have this way, this way, this way. Well, anyway, doesn't really matter. And now we can also look at the faces of the faces. And this is going to be interesting because we have d1 of d0 of sigma, or d0 of d1 of sigma. Then this thing is d1 of d2. No, d1 of d1 of sigma, or equivalently d1 of d2 of sigma. And this thing is d0 of d0 of sigma, and also d0 of d2 of sigma. Just because things are defined weirdly, but somehow it works out. Yeah, and the idea is, yeah, I don't know. Question is if we can sort of characterize our space X just using singular simplices. And well, we've sort of already defined these phase maps, and these phase maps are themselves n-1 simplices, or then n-2 simplices. But we would really like to look at not just one phase, but all of the phases, and sort of have some nice, I guess, some nice orientation preserving stuff there. So what we would really like to do is take linear combinations of phases. So
I have a slight confusion. If you're writing these based on directionality,
yeah,
or then shouldn't it be d0 of d2 sigma and d1 of d2 sigma like interchanged?
so the thing is, like d2 sigma,
Yeah.
we can just plug in a point, or like plug in one. So d2 of d0 of d2 of sigma is equal to sigma of d upstairs to d upstairs naught of the point, I guess. That's just by definition. No, one. Now what does d naught do? This is just d naught of 1 is just 0, 1. And then we apply d2 to that. So this is 0, 1, 0. And the other way around. Did I write things wrong? Oh. Maybe. Actually, I might have been. Could also be completely wrong about these things. Sorry.
No, I feel like you're almost correct. It's just interchanging the d0, d2 and the d1, d2.
You mean here a 1?
No, I mean the right hand side.
Here 1. Okay.
No, but I get the idea. So you can basically verify this, right? By doing the operation explicitly.
I guess this is the more instructive gist. It's not very intuitive how you draw these things, but in the end, you can always verify it by just calculating stuff. So now we would really like to take linear combinations of our simplices. And so we define singular n chain is a formal linear combination of n simplices. And we take this linear combination over, well, Z, because in essence, we just need to add and subtract them, and that's it. Over Z of n simplices. And we write it as Cnx. And yeah, essentially you can just say Z adjoined those X, but not as rings, but as abelian groups. And as I've already hinted at, we want to define a boundary operator that assigns to each simplex sort of its boundary, but like with the correct signs. So we would like them to preserve orientation. So what we would like to have, for example, if we have like a one simplex that is a curve that goes from here to here, with that endpoint and that endpoint being d0 sigma and d1 sigma, and this being sigma, we sort of want to have that our boundary map of sigma isn't d1 sigma plus d0 sigma, but d1 sigma minus d0 sigma. Oof, that was wrong. Should be these things. So if we have a map from here, a curve from here to the other point, we would like the boundary to preserve that direction. And similarly, if we have a triangle, with sort of faces, yeah, I guess we can label the corners and the vertices and the edges nicely. Then the edges have sort of a natural direction themselves, and we would like the linear combination again to sort of preserve the direction. So we want the boundary of sigma to be, well, we go in this direction. So we want it to be A minus B plus C. And well, how do we define this in general? For sigma and an n simplex, a singular n simplex, define the boundary of sigma to be linear combination of I from 0 to n minus 1 to the n di sigma. Should probably be an n plus 1, because if n is equal to 1, we want this to be d1 minus d0. Now we can use some sort of linearity, or we can define our boundary operator to be a linear operator, or like a group homomorphism on all n chains. Sort of, if we have some linear combination, then we can just define this to be that linear combination of the boundaries. So our partial, or I guess we could call it partial n, is a map from our group homomorphism from the n chains to the n minus 1 chains. And it's called the nth boundary operator. And well, the reason why I've also written lemma here is that we actually make a statement about this operator, namely it satisfies the sort of notion of boundaries not having boundaries themselves, namely delta n after delta n plus 1 is equal to 0. And I already see Mario laughing, because yes, this means we get a chain complex. Yeah, so chain complex of, well, actual chains and actual boundaries. Can you believe that? And this particular chain complex is called the singular complex of our topological space X. And well, I guess we can now reiterate our bit of terminology. Chains that have no boundaries are called cycles. So kernel of delta n cycles, and the image of dn plus 1. So those cycles that actually do come from our boundary operator are called n boundaries. And well, then we can get our homology groups of that singular chain complex. Hn, which is just the, Hn of X, is, well, the kernel of dn divided by the kernel, the image of dn plus 1, is called the nth singular homology groups. Nth singular homology group. And well, that is what people mean when they talk about homology groups of topological spaces. And we can see that, again, they classify to what extent our chain complex fails to be exact, or more especially the nth singular homology group classifies to what extent n cycles fail to be n boundaries. I guess one simple example to illustrate this, example would just be we take R2 without 0, namely we just exclude this one point. Then we can construct a cycle, namely by having E0, E1, E2. I guess you can also call the vertices names. So then the boundary of E0 plus E1 plus E2 is equal to, well, the boundary of E0 is C minus A. The boundary of E1 is B minus C. And the boundary of E2 is A minus B. And we can see we have plus C minus C plus A minus A plus B minus B is equal to 0. So we have E0 plus E1 plus E2 is a cycle, but not a boundary. again, well, you could say in a way we haven't really gained anything, because we still would have to show that like we can't fill this in a nice way. And that is certainly true, but we actually have more tools here at our disposal. It's a cycle but not a boundary, so H1 of R2 without 0 is not the trivial abelian group. So the reason why homology or singular homology is much preferable to what we did before, the stuff with fundamental groups, is that there are sort of a host of axioms that singular homology satisfies that are very powerful. And also, by definition, we are working with abelian groups here. So everything is already a bit nicer from the outset. Well, what are these axioms? Those axioms are called the Isenberg-Steenrod axioms. And they are as follows. First, homotopy. Says the following. If we have a continuous map F between two topological spaces, that one induces a chain map. CF from between the singular complexes of those two topological spaces. Just by, well, you have a simplex, and you can just map it to F after that simplex, which is then an n-simplex of Y. And this one turns out to be a chain map, which means that it induces group homomorphisms between the homology groups. And they are factorial. Now, what does homotopy say? Homotopy, or the actual axiom, says if two maps are homotopic, then the chain maps induced by them are homotopic, as in chain homotopy. And therefore, they induce the same maps on the homology groups. And, well, this implies that if the spaces X and Y are homotopy equivalent, then their homology groups are, well, the same, or at least, let's say, isomorphic. The second axiom is called excision, and it basically relates to relative homology, because we can sort of, if we have a subset, we can tell our homology theory to ignore all simplices that lie in that subset, and that's called relative homology. And then excision says, if we have a subset of that, we can sort of cut it out of both spaces and relative homology stays the same, which in itself seems to be sort of obvious, but yeah, I don't know, I'm not writing it down because it's not particularly helpful if you are introduced to it as a first thing. So third axiom, dimension. Well, that's a bit misleading. It tells us that the space containing one point, that this one has very specific homology groups, namely the following. It is Z if n is equal to 0, and the trivial group otherwise. The fourth axiom, additivity, basically tells us if we have connected components, or if we can decompose our space to be like the disjoint union of other topological spaces, then the homology groups are just additive. And number 5, the one we've all been waiting for. Well, it's called exactness, but like it's not exact. It's more exact in the sense that we get a long exact sequence. Yeah, I guess can't really work around relative homology any longer. So if U is a subset, note that it doesn't have to be open. It can be any subset. And then we can view it as a topological space if we just give it the subset topology. Then we have an exact sequence between chain complexes, where we just define Cn of x comma u to be Cnx divided by Cnu. This is what I've mentioned earlier, relative homology, where you sort of ignore all of the simplices that lie in U. Is exact. So now we have a short exact sequence of chain complexes, so we get the long exact sequence of homology. Namely, we have the nth homology group of U, then the nth homology group of X, then the nth relative homology group of X relative to U, and then we have the n minus first homology group of X of U, and so on. And well, usually we look at this for a very specific case, namely the so-called Mayer-Vietoris sequence. If we can write X as a union of two sets, more specifically as the union of their interiors, then we have a short exact sequence between like the intersection and then the direct sum, and then something that is called blah, blah, blah with an open cover. But this one is actually homotopy equivalent to Cx. Is exact, meaning that we get a long exact sequence. That sort of looks at these intersections, and then the direct sum. And then just homology of X, and then one dimension lower, and so on. And this is like the most powerful tool ever, because like, I mean, this is sort of similar to the Seifert van Kampen theorem, I guess, in that we are also looking at like, you have two spaces covering a bigger space. Let's see how this relates to homology, but like, I don't know, much nicer. We can again look at our example of the spheres.
Philip, can you just scroll up a little? I just have one question to ask.
Yeah.
Like more up. Yeah, here the fact that you said that if the chain homotopy, if their chain homotopy is equivalent, then their homology groups are the same.
Yes.
What is the implication of that? Like, is homotopy equivalence and homology the same thing?
No, so the thing is, we have two homotopic maps, F and G,
Yeah.
and those induce maps on the singular complexes. Chain maps, and those chain maps are homotopic in the sense that we define chain maps to be homotopic in the lecture about homological algebra.
Okay.
This is just some very algebraic notion, but it has the desired effect that they in fact induce the same maps on homology.
I'll watch the last lecture then.
If you really want to.
Yeah.
Okay. So now we are just going to routinely derive all of the homology groups for all of the spheres, because we can just do that. Like fundamental groups of spheres are just the worst. We've described the first fundamental group, or the fundamental group, but sort of the higher groups of spheres, that is firstly non-trivial, and secondly still an open problem, like a very hard open problem. But for homology, we can just do that. We can again write our thing as the union, our sphere as a union of the two semispheres, where again the northern and the southern hemisphere, well, they are homeomorphic to the disk, and the disk is contractible, so they are homotopy equivalent to just a singleton set. Hence, by the dimension axiom, we have that the mth homology group of the nth hemisphere is just Z if M is 0 and the trivial group otherwise. And we have that the intersection of the two hemispheres is homotopy equivalent to the n-1 sphere. So now what does the Mayer-Vietoris sequence look like? Well, we have the kth homology group. Okay, yeah, I'm going to, so the sequence is going to look a bit weird. And especially we have to distinguish between sort of the very end and somewhere more in the middle, or like somewhere before the end. So we have for k is bigger than 1, we have sort of the middle term, then hk of Sn, and then the beginning again, but now one dimension lower. And I guess we need one more. Dot, dot, dot. So now we know that the hemispheres are homotopy equivalent to the disk or to the point. So that is equal to hk of the singleton set. And this one is also equal to hk of the singleton set. But since k is bigger than 1, this is just a trivial group. So we just have 0 here. Since k is strictly bigger than 1, the same argument also applies here. Which means that the kth homology group of Sn is indeed isomorphic to the k minus first homology group of Sn plus intersection with Sn minus, but that one's just isomorphic to hk minus 1 of Sn minus 1. And I guess we also have one last thing. We have okay, I didn't actually write that one down. But I guess if we look at k is equal to 1, then this thing looks like, well, we start at 0, then we have h1 Sn, then we have h0 of Sn minus 1, then we go to basically z plus z, and then we go to h0 of Sn, and then we go to 0. And basically you can do some, I guess, on one hand, you could do some magic to just find out what this means in particular cases. But I guess the easier way is to just spoil a bit what comes later. Because it turns out that h0 actually just classifies the connected or the path components. So we can just write down what h0 of the n sphere is. Namely, it is z squared for n is equal to 0 and z for n is bigger than 0. And I guess we can also write down one more edge case, namely hk of S0, because S0 is just 2 points. So hk of S0 is hk of the singleton set, co-product with the singleton set, then we can apply the addition axiom and say that this is just hk of the singleton set, I guess plus itself or squared. Jesus. Which is just using the dimension axiom, z squared if k is equal to 0, or the trivial group otherwise. So I don't know if you sort of want a bit of a diagram. If we have k here and n here, so the n sphere and the kth homology group, then we have a relation telling us that we can reduce in that direction, and then we know what it looks like. So that direction, and we know what the homology group looks like on this line and on this line. So we have defined everything, or we have found everything inductively. I guess the difficulty comes in writing it down, but ultimately our finding is that hk of Sn is, well, we have z if n is equal to k and both are non-zero. We have z squared if n is k and they are both 0. We have z if k is equal to 0 and not equal to n. And we have 0 otherwise. Okay. I have a bit more stuff to cover actually. Yeah, I guess 2 things to mention. I've already said that H0 sort of classifies path components. Oh, okay. Bye. Secondly, H1. Well, it sort of looks like paths. I mean, one simplices, we're looking at one simplices that sort of have no surface or no boundary, meaning that their endpoint is equal to the point where they begin. So sort of looking at loops, and like everything is fine with homotopy, so sort of looks like the fundamental group, right? Well, there are 2 caveats. Firstly, pi1 is non-commutative or non-abelian. But H1 is very much abelian. Or put differently, sort of, if you traverse paths in different orders, it matters in the fundamental group, but it doesn't matter in the first homology group. And secondly, is what I guess a bit mentioned, but not really. Pi1 only sees the path component that our base point x is at. So, I mean, sure, you're looking at loops that start at this point, so you can't leave the path component you're looking at. Only sees one path component. Whereas H1 just sees all of them. But it turns out that those are really the only 2 abstractions that stand in the way. Or put differently, if x is path connected. So if there is only one path component, then H1 is, well, not the fundamental group, but it's Abelianization. And what is that? Well, this is the most general abelian group obtainable as a quotient of pi1. It is pi1 divided by its first derived group. Meaning you just take all of the commutators and then set them to 1, basically.
Like you're symmetrizing it basically, right?
Not symmetrizing. It's sort of, you have the same generators, but now you say they all commute.
Yep.
So I guess in that way, maybe, yeah. That was just, I guess, one last thing I wanted to mention. Now we can look at the final example that I already promised at the beginning. Golas is already going to moan. Klein Bottle. So, what is a Klein Bottle? Well, a Klein Bottle is just a square where we identify sort of faces on opposite sides in different directions. So you can write it as we identify those faces in that direction and those faces in opposite direction. And well, it is sort of well known that we can, I've not even drawn a square, Jesus. And now it's sort of well known that we can cut such a thing into Möbius strips. And that's what we'd like to do. Because ultimately you can contract the Möbius strip so it's isomorph or homotopy equivalent to a circle. So how do we cut this up? We cut it along this one contiguous line. Why is this just one line? Well, we can go up here, this point is equal to that point, and then just go on. And then when we land here, well, this point is just that point, but that point is just this point. Questions? So, we call this thing U and this thing V. Yeah, I guess I called the space K. K is a union of U and V, where the intersection of U and V is just this line here. And I guess, as I've already demonstrated, is just a circle. So it is homeomorphic to S1. And we also have that like U and V are homotopy equivalent to S1. Because we can just contract them to one line. Now, which line would that be? It's not as obvious as just saying a line going down the middle, because, well, that point isn't the same as that point, or is it actually? Huh. Oh, it actually is. No, sorry. That point here is that point there. Okay. Yeah. Can just do that. Can just contract them down to those lines. And that's it. So what does our Mayer-Vietoris sequence look like? Yeah, I guess this is also an example of things aren't maybe trivially obvious just by looking at the objects inside that series, inside that sequence, but you also actually need to look at the maps. So yeah, randomly I'm starting at the second homology group of the intersection, meaning S1. Then we have H2 of U, direct sum H2 of V, and then we go to H2 of K. Then we go to H1 of the intersection, and we go to H1 of K, and then we have all of the H naughts. Oof. So now we actually know a whole lot of stuff. We know, for example, that the second homology group of the one sphere is 0, 0, 0. We also know that the 0th homology group just characterizes path component. So K is path connected, Z. The one sphere is path connected, so we have direct sum of Z with itself. And again, the one sphere is path connected, so we have Z. And okay, so what would we like? I guess we can also fill in the first homology groups. That thing is also Z, that thing is Z, that thing is Z, and that thing is unknown. So now if we look at a certain subsequence of this, we have 0 goes to the second homology group of K, goes to Z, goes to Z squared via some map F, where this was the homology group, the first homology group of the intersection, and this is the H1U plus H1V, and so on. Now this map here is injective. Sorry, this map here is injective, so we can see H1K as a subset of Z. And then this thing is exact. So we have H2K is the kernel of F. So now, what does this F do? Well, F basically embeds, well, basically we have a circle. I think I have to draw this again. So we have our Klein Bottle with its 2 Möbius strips. So now if we define sort of our isomorphisms nice and coherently, we have that this group here, the homology group of the intersection, is generated by the cycle, or by the line that just goes once around. And this map F just sees it once as a chain or as a simplex in U and as a simplex in V, and just sees what does this, what class is this. But now if we see this as a map in V can actually contract this, or as a map in U can sort of move it around a bit. And then it looks like something that goes around twice. And similar, if we view it in V. So what does this thing do? F maps some number n to 2n to n. And this means that F is injective, and that therefore its kernel is the trivial group, so H2 of K is the trivial group. Note, however, that if we allowed our coefficients to be, for example, in Z modulo 2, then F would be the zero map. Therefore, everything would be its kernel. So then the second homology group of K with coefficients in F2 would be F2, which is, I guess, precisely the statement that it's non-orientable. But we're not done yet. Because next can look at another subsequence of the Mayer-Vietoris sequence. Namely, we have, well, basically just what comes after that one, z squared to h1 of k to e to z squared and so on. So this one was the homology group, first homology group of U and the first homology group of V. We call this map G and this map H, and that was just zeroth homology group. Now note that these maps here are injective, I think. So that map here is injective. So its kernel is 0, meaning that the image of H is 0. So H is just the 0 map. But now because we are exact at this thing here, this shows that H1K is the co-kernel, I believe. Is that correct? No. So H is 0, meaning that the kernel of H is, well, H1K, meaning that this is equal to the image of G. And the image of G, Jesus, this is really getting algebraic here, because the image of G, well, we can just say that this is equal to the domain of G divided by the kernel of G, by the isomorphism theorem. So what does G actually do? Oh, Jesus, we don't even need that, because remember we had our map F before here. And so then we can use exactness there to see that the kernel of G is just equal to the image of F. So I guess the upshot is that H1 of K is equal to Z squared divided by the image of f. And what was the image of f? Well, that was basically z times the vector 2, 2. Yeah, this f. So what is this isomorphic to? Well, it's isomorphic to z's direct sum z over 2. And again, we have a sort of an echo of the non-orientability, because we have this, well, essentially we have this path that squares to 0. But I don't actually know which path it is. Yeah, I guess the last part was just the last part that I still have in my notes is just that these homology groups, they help classify maps. Well, classify maps up to homotopy equivalence in a way, or up to homotopy. And this gives rise, when you're talking about spheres especially, the maps between spheres can be uniquely characterized by the map that they induce on the nth homology groups, if we're talking about the nth sphere. But since those are just group homomorphisms from Z to Z, they are uniquely characterized by one number, and that number is called the degree of the map. And the degree of some map is in physics also called a topological quantum number, or the topological quantum number. And I guess this sort of ties in nicely with something I did in SPCMT extension, where I precisely talked about this topic, but never mind. Yeah, I guess that was it.